from India.
We are participants. Now we are on the second day, first session.
One of them, you know.
And we are on the second day of the first session for this ATAL. And our ongoing speaker is the same as the previous day's speaker, Honorable Dr. Shibendu Shakhar Roy, Professor of Mechanical. Today he will present the continuation of the previous lecture. So, hope we shall increase ourselves in the knowledge of this lesson. Thank you.
Okay, good morning everybody. So let us start today's topic. It's as Dr. Kamal mentioned, it is the continuation of the yesterday's topic. Today let us focus on one of the application of robotic system in manufacturing, and more specifically the robotic 3D printing technology. This is also a part of or one technological aspect of the Industry 4.0. So Industry 4.0 part will be discussed on the 26th, maybe on 26th by Professor Gautam Sutradhar. And here I like to mention only one of the technology within the area of Industry 4.0, that is the 3D printing technology. So that means point. So we are focusing on here the 3D printing technology, and more specifically the robotic 3D printing. So before going to the robotic 3D printing, we like to introduce what is 3D printing. So 3D printing actual technical name is additive manufacturing. It is under the 4th industrial revolution. As you know, most of us are mechanical engineering. So mechanical engineering manufacturing process are broadly classified into these two. First is the formative manufacturing, which is also known as near penetrant manufacturing. If initial state of material is liquid with the casting and the injection molding, if the powder state is powder metallurgical method. If the initial state of material is solid, the metal forming, there are the different type of metal forming first. Next class is the more accurate after formative process. You have to go through the subtractive manufacturing process or material removal process, maybe conventional machining or unconventional machining, or maybe the hybrid machining. Next is the joining process like the welding, brazing. So these are the different joining processes. So this is the 3 classical manufacturing process. Your additive manufacturing is the youngest member in the manufacturing family, your mechanical manufacturing family. Today we are focusing on that. So once upon a time, it was a dream for manufacturing technologists to develop such a technology which has the potential of directly converting the CAD data into the real object. That means the technology provides the bridge from the product conceptualization to product realization in reasonably faster manner. That means rapid creation of the physical model. Now it is in reality in the name of additive manufacturing. And additive manufacturing is a manufacturing process of joining materials to create the object from the 3D CAD model data, usually layer upon layer, depositing the material layer upon layer. It is opposite to the subtractive manufacturing methodology, and this definition is proposed by American Society of Testing and Materials. And additive manufacturing is very similar to the way our nature is manufacturing many things. If you see the bank of river, there is a years after year, the soil will deposit and it will create a island kind of thing. So this is a good example of the nature by which they manufacture many things which is additive in nature, not subtractive. Even you see the plant, insect and human, everything adding material, not by subtracting material. So that concept has been here used in additive manufacturing. Very simple way. Let us say like to create this sculpture model. One thing you can do to manufacture this sculpture model: take a block with size more than this, and using the CNC machine or artisan, using a traditional tool by removing the material, it will give the shape like this. So this is the traditional way to manufacture this one. But instead of that, if you have that data or information, you make if you have each layer cross-sectional geometry available. That means if you know from bottom to top, if you divide into say 1,000 layers, and each layer cross-section might be different, and each layer cross-sectional geometry is known. Take a piece of a cardboard and cut that particular cross-section according to the cross-sectional geometry and add one upon another. Then also you can create this complex object. This simple concept has been used in additive manufacturing. This simple principle is used in additive manufacturing. First you have to develop the 3D CAD model of an object that you like to manufacture. Then you have to slice it by slicing software. Okay? What does it mean? If this is the CAD model, you slice it. That means you create 3D fast, then convert 3D into number of 2D geometry. First you have created the 3D CAD model, then by slicing software, you are creating the number of 2D cross section. As you know, the intersection between the line and the plane and the solid is basically a cross section. Now, according to the cross-sectional information, you will deposit the material over the platform. So, over the platform, you deposit the material, or depending on the process, you have to deposit the material, or you have to pass the laser ray or something in that I will discuss. That it depends on the methodology. But layer on layer, the material will be deposited, or material will be cured, or material will be sintered. Okay? And this way, the 3D object will be created. So that means wherever material is required, you have to add. So that is the difference between the subtractive manufacturing and additive manufacturing. Subtractive manufacturing, you have to take a block, then you have to remove the material to give the shape of your product, and that is the wastage in the form of chip. But in case of additive manufacturing, I will mention wherever you need the material, wherever there is a cross section, you add the material. So material wastage is less. Here also material wastage, because many cases support structure is required. So but material wastage is less in case of additive manufacturing process. Next is the general steps involved in additive manufacturing or 3D printing. First thing, as you know, you have to develop 3D CAD model of the geometry. So this is the only manufacturing process which will not work without CAD model. If you don't have a CAD model, then 3D printing will not work. Other manufacturing process will work by manually or semi-automatically, but additive manufacturing process without 3D model it will not work. So that is why it is mandatory to develop a 3D CAD model. It may be by using 3D CAD modeling software or by reverse engineering method. So once you develop 3D CAD model, after a lot of doing topological optimization, lattice structure design, so these are the now modern areas in additive manufacturing or in design. Then you have to save your file into a neutral file format, which is well accepted for file format is the DOC, STL file format. That file will be imported by the slicing software, and before slicing, you have to orient your part, geometric model within that volume, so that your requirement of the support structure part I will discuss. Wherever there is overhead portion in the product, some manufacturing process you need support from the bottom. So depending on the orientation, requirement of the support structure depends. So that is why you have to orient your object judiciously so that number of support structure should be as less as possible. And after that you have to specify the material, different process parameter, and then you do the slicing using the software, slicing software. This is called the pre-processing. Once the pre-processing is over, slicing is over, that means you have converted your 3D model into number of 2D layers. That 2D layers information will fed to the machine, additive manufacturing or 3D printing machine, and it will print the product by depositing the material or by curing the material or by sintering the material layer by layer, and you will get the build part. The build part, whatever you will get, that is not like your functional part. You need certain type of post-processing operation like cleaning, post-curing, or the post work and finishing, depending on the process you will use, and ultimately whatever you will get, that will be component for prototype. Previously it is mostly used for prototype, that is why it was called that time rapid prototyping. Now it is not restricted within the prototyping. It will act as the product will act as a pattern for the complex component, and modern additive manufacturing process you can use the 3D printed component as a functional component. So this is your general steps involved in 3D printing or additive manufacturing process. Now if you compare the 2D printing and the 3D printing, it has the similarity. Like here in 2D printing, first you have to prepare the digital document, then you fit to the machine. Here I like to give example of your inkjet printing system. In inkjet printing system, inside there is a ink chamber. Printhead consists of a tiny nozzle, array of tiny nozzle, maybe the 10,000 tiny nozzle in an array. It will act as a printhead like this. There is a printhead inside, and the tiny nozzle is arranged here. Now it will move like this, and paper will move this way. So if this movement is X movement, paper will move Y direction. Because of the X movement and Y movement, and selectively it will deposit the ink, you will get the one printed copy. Same thing happened here. In 3D printing, first you have developed the digital model, that is your CAD model. After slicing, it becomes 2D, number of 2D geometries according to the one 2D. Here it is 2D, no? X movement and Y movement. That 2D, that is, you can say 2D printer. Now here, first you convert the 3D into number of 2Ds. Each 2D you take at a time. Same type of heads, head material will deposit. But here the paper will not move. Over the platform it will deposit, one layer is over. But when it is not only X movement, here head having, in this case head having two movement, X movement as well as Y movement simultaneously, to get the 2D geometry. X and Y movement will be given to the head. And table, initially it will be stationary, it will deposit one layer, then table will move downward direction. It is intermittent motion. The build platform having intermittent motion. Truly speaking, it is 2.5 movement. XY movement and intermittent Z movement. As there is 3 movement, and ultimately you get the 3D object, because once one layer is over, platform is rolled down, second layer is deposit, again platform is rolled down, third layer is deposit, then again platform deposit like move downward direction, and this way 3D object will develop. So this is the basic principle of 3D printer. Now, depending based on the initial form or initial state of raw material, additive manufacturing process classified into 3 groups, though this classification is obsolete one. Liquid based additive manufacturing, so initial state of material is liquid, generally the liquid resin is used. The first additive manufacturing in the world is SLA, stereo lithography apparatus. After that, many other additive manufacturing developed in the different companies. Next is the solid waste additive manufacturing. Here, initial state of material is either in your paper form or in a filament form. Like loam is the paper form, laminated manufacturing, FDM is the filament form, fused position modeling. But most promising one is the powder based additive manufacturing, where the initial state of material is the powder. It is also very close to your powder metal based method. And selective laser sintering is such a method. Your 3-dimensional printing is a method. Discuss about a little bit of all the methods. But modern classification again based on ASTM, based on the methodology used to create the layer. it will be classified into 7 groups. First one is the photopolymerization based method. SLA, photopolymerization name itself has mentioned that the initial state of material is the liquid resin, which is photoburnable. Second one is sheet lamination. Again, the initial state of material is the sheet form, that is your name is sheet lamination. Third one is the material extrusion. Here the initial state of material is the filament, material extruded. Next is the binder jetting. Is the powder over the binder will deposit selectively. Powder bed fusion. Here powder over which laser you have to stress it. So laser using laser it will fuse the powder and it will create it start the sintering process and create the layer. Next is the material jetting. Here again liquid material will jet and it will cured by the laser. Directed energy deposition is more specifically the metal additive manufacturing process. Again it is either powder based DUT or the wire based DUT. So these are the manufacturer of the additive manufacturing of this methodology. Till date the same methodology available in the public domain, but there are many other methodologies which is not yet in the public domain because it is one of the most promising areas in the manufacturing and it is a very important component in industry 4.0. So the method I mentioned here in nutshell has been shown. Within that there are some variety also there, like that photopolymerization, SLA is there, DLP is there, CDLP is there, like the different varieties there for each category. Now, application of additive manufacturing, quickly I like to show you few applications. So here, most of the automobile industry, aerospace industry, or any kind of product development industry is a user of this product in the design department, even now manufacturing. So you can create your own tools, the RPs, you can create your kind of prototype for the design verification, for architecture. Every discipline there is application of additive manufacturing currently. Each and every discipline, engineering, non-engineering, everywhere. Biomedical, fashion accessories, shoe industry, even you can manufacture your own logo. So possibilities are endless.
3D printers are changing the world we live in. They allow us to imagine and create works of art in a new way which was never before possible. This new technology can also reduce costs.
So this is also very fast 3D printing. But let's show some traditional 3D printed component.
Number 10, the walking gyroscope.
So this here the most of the components are 3D printed. This type of mechanisms can be used in a mechanism lab.
You can even build your own, since the 3D model can be found on thingiverse.com. So make sure you check my description and click on the link to this 3D toy. That's number 9, the CNC.
So here the CNC machine, few components are 3D printed.
The CNC machine is mostly made from 3D printed parts and is a lot cheaper than your average machine. It can work with woods, plastics, and even some metals. So I think I'll make sure not to incorporate an AI program into my next 3D printer creative robot revolution. And like the last object, it can be found on thingiverse.com. At number 8, the
So this one is very interesting one. There will be no such itching problem for this kind of plaster. And for that, the digital model of the shape of the hand is required, and that can create from the CT scan data.
So this is definitely innovative and very beneficial to people who have to deal with an injury. At number 7, the Kobe King Jones.
So
The 3D printed
loudspeaker is little bit complicated shape loudspeaker.
This small speaker array gives off great sound while being exponentially cheaper than some of its commercial counterparts. I expect they see and hear pretty cool 3D printed speaker houses in the near future. At number 6, the
So this to decorate the room or lighting system of the room, this complex separate object manufacturing is extremely difficult by traditional manufacturing process, but it is very relatively easy for the additive manufacturing process.
endless when it comes to 3D printing. At number 5, the 3D printed 22RA4.
So this is the Toyota in replica.
It's actually a replica composed of many 3D
It is created by the 3D printed component.
Once again, visit diddyverse.com and print your own replica engine, but it'll likely take you over 70 hours to print. Every part goes, and it's driven off an electric motor. And if this is not crazy enough, the same creator even built replicas of a 5-speed transmission and a transfer case. So that's pretty crazy. At number 4, the locomotive's 3D
We have seen the newspaper, the 3D printed cars, there are many components manufactured by the
exterior body and interior
3D printing. Polymer 3D, sorry, your component 3D printing and the metal 3D printing. Polymer component and metal 3D printing.
It's a fully electric car with a top speed of 50 miles per hour, and it's expected to be released next year. At number 3, a real 3D.
So this is the application of metal 3D printing. The JC being manufactured by metal 3D printing method.
Printing methods can cut costs and production times. Its creators are hoping to test fly a prototype within 10 months. If everything goes well, commercial certification will be awarded in the next 2 years. 3D metal printing is a fairly new thing, and it'll not only improve engine building times for the aviation industry, but also for the automotive and marine sector as well. At number 2, the portable.
So this is the application of 3D printing in the civil engineering and architectural engineering. So this is very important in respect of the robotic 3D printing, because the civil engineering structure or the architectural structure is huge. It is not a smaller one like mechanical engineering. Structure is huge here. If you like to use 3D printing technology, you have to switch over to the robotic 3D printing. There is no way out. So this is a 3D printed house in China. Similar kind of a house already developed in India by a company called LSD. So in Dubai, so 3D printed office. So Dubai is the first 3D printed office. This is the application of robotic 3D printing, because as I mentioned, the civil structure is huge one, a bigger one. This is an example of robotic 3D printing. Robotic arm that I have discussed in the last class is used here for depositing the material layer by layer to create the big structure, big civil structure. As this is geometry complex, so it is controlled by the computer. Okay? So that is why it is robot. It is not a other thing. It is basically a giant robot. So these are the 3D printed buildings developed using the robotic 3D printing or 3D printing robots. So if you see the very close view of the deposition head, so deposition head will deposit the special type of your concrete material to create the work of the building. So this is the deposition head in the 3D printing used in civil engineering. See here. Jewelry industry, like to skip it. This is 3D printing is also used in jewelry industry, but I like to skip all this thing. Another important application of 3D printing is the biomedical industry for implant development, even for the artificial organ development, bioprinting. But still it is the research phase. But the organ developed by the biogel used for practicing the surgical thing by the amateur doctor and for educational purpose, but it may be in near future the 3D printed organ is replaced with the human body. With that hope, the 3D printing scientists, or more specifically bioprinting scientists, are working in that direction in the development. So I like to skip this video. This is the 3D printing is also used to create the wooden gate or the toffee like here. So here also I like to design inside the honeycomb structure or square honeycomb structure is developed. Manufacturing this one is very difficult in traditional, even impossible for the your traditional manufacturing process. From outside it will be continuous, but inside there is a honeycomb kind of structure. So getting that one by traditional manufacturing process is not possible, but you can easily do by additive manufacturing process because you are developing material layer by layer, not as a considering thing in 3D. This is another kind of robotic 3D printer. Configuration is a delta configuration, not the serial manipulator. It is kind of your parallel manipulator. So it is the example of a parallel manipulator for 3D printing. This is also kind of robotic 3D printing where delta configured parallel manipulator is used. So two types of robot have been used in 3D printing. One is the serial manipulator, biggest example, and here it is the parallel manipulator, the delta configured. Three D printed food. This is another application. It has a lot of application for the for astronaut in the space. They are using the 3D printer for their preparation of the food during their mission. This is also interesting area in respect of the additive manufacturing. So let us skip this particular part. So like this type of 3D printer will carry by the astronaut. So this is a NASA project actually. Okay, so next we like to discuss about the working principle. Till now I have discussed about the application. Now quickly like to discuss about the working principle of the 7 different principles. And parallel like to application of additive manufacturing. The first one, many of you know this, the sheet lamination based additive manufacturing. That means the method is low. It is also very old method, but it is not a for additive manufacturing, but it is very simple to understand the principle. That is why I have chosen this one, the first one, to discuss the principle. In this case, it is a solid based and first developed in the year 1991 by Belisis, and material is solid sheet coated with heat activated adhesive, that means thermoplastic adhesive. Here it is the sheet bundle, the paper. Back side there is a adhesive. But it is heat activated. If you apply heat, then only it will activated, not before that. Now, I like to pre-processing part is same. That means you have to develop CAD model, save .html file format, then you are slicing. After that I am talking about. After that, so over the machine, in this machine, this is the build platform. Build platform initially at the here, and over the build platform there is a white dummy paper. You have patterned the dummy paper using say sellotape or something like that. And from this roll, that is the material supply roll, you pull the roll over there and you have to clip over the takeoff roll. This particular platform, the fresh paper will be here, and below this paper there is adhesive. Now what it will do, the process, first it will do this particular laminated roller will pass. This is the roller, is a heated roller, and it will create the force of pressure. It will move over this fresh paper, and because of the pressure and temperature, adhesive below the paper will activate and it will adhere with the previous layer. Once it is over, next you have to make a process. Suppose you like to manufacture a component. Suppose we manufacture the component like this, though I have not drawn the engineering drawing, simply representing this. So if your first processor is like this, you have to take, the slice, you have a slice data. Let us say first layer processor is like this. What you will do? There will be laser system, laser source and laser X-ray positioning system. It is basically mechanical type X-ray movement, or it may be optical type movement. Optical laser scanner. It is called the optical laser scanner. So laser will scan. That means it will control the X-ray path. Laser will stressing over the outer boundary and the inner boundary. And due to the interaction of the laser and the paper will cut the outer boundary and inner boundary. Another thing we have to do in this case, depending on the highest size of the cross section, you have to take one rectangle, big rectangle. Highest cross section bigger than that, one rectangle you have to cut. Because whenever the platform will lower down, with this total rectangular area, it will lower down. Now unwanted portion, this inside it is hollow. At the hollow inside paper is unwanted portion. Unwanted portion you have to cross hatch. Here also outer side this is the unwanted portion. Unwanted portion you have to cross hatch. Cross hatch means you have to making that particular area in a small pieces, because you can easily remove that small pieces after completion of the product. That I will show you. So once one layer is over, build platform is lowered down equal to one layer thickness. One layer thickness means the thickness of the sheet. One layer thickness is the thickness of the sheet. Once it's lowered down, then takeoff roll will rotate. Takeoff roll will rotate. Then the fresh paper again it will cover the previously laminated layer. Once the fresh paper will reach here, then your laminated roller again pass, it will create the lamination of the second layer, and according to the second layer cross-sectional information, the laser will trace the outer boundary, inner boundary, outermost boundary, and the unwanted portion crossed hair. So this process will continue till top of the paper. Okay? So this is a very simple lamination process. And ultimately, whatever product you will get, I will show this is the ultimate product you will get, like this box. Now remove the unwanted portion, and you have small cross hair that it will remove by small tiles. You can easily remove. Otherwise, due to the solid form, totally solid form, removal is not that much easy. So that is why you have to cross hair so that you can easily remove the small tiles. And obviously here wastage is huge wastage in this case. Wastage of material is huge. So this is the machine, though it is the animated version of this machine. Here the extra movement is mechanical extra movement of the laser, but modern days it is the your laser scanning system, optical scanning system, laser optical scanning system. So this is the laser head tracing the path according to the cross-sectional information. You just see, this is the paper. After lamination, there is a cutting using the laser. Once it is over, platform will lower down equal to 1 layer thickness. Then again, paper will move. Hot lamination will take place using the roller. So this process will continue till top of layer will come, and ultimately you will get the product like this. And if you see that you have to remove by this method, this very traditional remove. So this is the machine. The machine I am showing you it is purchased long back in Senior Dudapur. That is the first machine. I have introduced this particular field with this machine only in the long back in 2001. Modern machine, I have to show quickly that this modern machine of based on the laminate of the manufacturing is this one. It looks like a 2D printer. Same way, but here the sheet is not the paper sheet, it is a plastic sheet. Plastic sheet is used, but process is same lamination process, sheet lamination process.
Allows you to position the printer right in your office, even on your desk. The easy-to-use LDU software provides quick, easy setup to begin building your model. Building layer by layer until the model is complete.
Same machine you see, here also extra movement. But here mechanical type of extra movement of the laser. So here I like to tell about one thing. Any process there is a process parameter. These are the process parameter for roller temperature. And you know mechanical engineering know any process having the process parameter like in machining, cutting speed, feed rate, depth of cut. Here also the roller temperature, roller speed, and the different cutting parameter, roller diameter, and the edge size and the sheet thickness. And every process has the pros and cons. Here also in case of here advantage is low thermal stresses and the different color part can manufacture multi-material component is possible. Low cost but huge wastage of material, poor resolution, difficult to manufacture hollow part. This is the disadvantage. Now it's break for 5-10 minutes. Thank you. So next we'll discuss about the remaining 6 additive manufacturing process. And its picture is this is the machine, and obviously CAD model is required. The computer system is integrated with this machine. And this machine has been developed by Hull, and he founded his company 3D System. So 3D System is the first company who manufactured the 3D additive manufacturing system, and that time it was called the Rapid Prototyping System. So this process is based on the liquid material. Initial state of material is liquid, that is photocurable resin, and or it may be the epoxy resin or acrylate resin, and laser is used. The laser is used to start the curing process. Helium cadmium laser or the argon ion laser. Now the diode laser or the fiber laser is used now in a modern machine. But whatever I have mentioned here, the old machine that use this type of laser. So, in respect of the additive manufacturing, laser is very important. So, without laser knowledge, it is very difficult to go into the detail of the additive manufacturing process. Now, in this particular process, after pre-processing, I like to explain. So, here it consists of a vat with a full of photocurable resin. Now, build platform initially will be here. And over that there is a thin layer of liquid resin. Now how much thin it will be? As during the slicing process you have to mention the layer thickness. If your layer thickness is 0.01 millimeter, the layer thickness you have to specify in your pre-processing stage where you will do the slicing. During slicing you have to specify your layer thickness, because layer thickness has a lot of contribution to the product quality. So that is why layer thickness is very important. So depending on the layer thickness you specify in your slicing process, you have to keep your platform at such a height. Over that one thin liquid resin will be exited. That thin liquid resin thickness is equal to say 0.01 millimeter. Now next what you have to do? Now over that you have to trace the path. Laser, there is a laser. This is the laser, and this is your optical laser scanning system, so that laser will tracing the path. So I am explaining here. This is your platform over which there is a liquid resin. Now this is the laser. Laser will move in XY plane. Okay? If my cross section is like this, it will trace only, if you see, if I do the tracing only the outer boundary and inner boundary, due to the interaction of the laser and the photocurable resin, it will create only this line and this inner boundary and outer boundary. Is it serve your purpose? No. Because
I need this cross section. No? This is solid cross section. I want this solid cross. This cross section is solid. Hollow portion is this one. So in order to make the solid cross section, you have to laser should trace inside also. Then only the interaction of the laser and the liquid resin will create the solid cross section. Got my point? Previous case it was the paper itself is solid. Only the outer boundary, inner boundary cutting is sufficient by laser. But in case of a SLA, you have to stress the laser inside also. Laser path you have to follow inside so that it will cure the complete cross section. So that's the difference between the laser path in SLA and the laser path in the low process. So due to interaction of the laser and the resin, photopolymerization process start and it will cure or partially cure initially, and once one layer is over, platform will lower down equal to one layer thickness, that means 0.01 millimeter by CNC system and screw nut mechanism. Now liquid resin surrounding the first layer, it will cover the first layer, but that process is very slow. To make it very fast, a leveling wiper, a leveling blade will move from one end to another end so that it will report the new layer of the resin, and thickness is equal to 0.01 millimeter. Now according to the second layer cross sectional information, again the laser will trace the outer boundary, inner boundary, and also inside pattern. There are the different company use the different pattern, or you have to select the different pattern on which the laser will trace in the path. You may inside you may follow this particular pattern, or what you can do, you can use this pattern to tracing the laser inside. So it is up to you which particular pattern you use to trace the laser inside the cross section to cure it. And strength is depends on this also. That's very important. Strength is depend on this. So second layer is over. This process will continue till topmost layer will come, and ultimately you will get the product like this. Again, this machine is available. It's first machine in Eastern India, which was procured by Siemens in the long back, maybe before 2000. So this one I like to tell you the giant machine, the bigger machine, the SLA machine, stereolithography apparatus machine. So this is the pre-processing part. So this is your laser stressing. Liquid resin. So one layer is over, platform is lower down, reporting blade. Again laser stressing. This process will continue. Next, what to do? Platform will move upward direction. So partially cured component, you can take it out from the vat with the liquid resin. Now this particular component is partially cured, not fully cured, because it is within the resin only. What you have to do? You have to do post-curing operation, that is post-operation. You have to keep this particular component in another chamber under UV light, so that it will fully cure and you will get the full strength of the material. And overhang portion, you see, overhang portion, there are a lot of support structure that you have to remove. Overhang portion, a lot of support structure. Why support structure is required, that I will explain. So these are the support structure. These are the support structure that you have to remove. Overhang portion, you need support structure. So that part I will tell. This is the product developed by SLA process. Now first I like to tell about the support structure. Though I have chosen a very simple example to understand the requirement of support structure and how you can eliminate the support structure in some cases, but it is not avoidable many times. Suppose your part orientation is like this. Part orientation is like this. So this is some part orientation like this. You have to manufacture this part. Now if you do the slicing, this is your build platform. If you do the slicing, so let's say this is the slicing. So this is your slicing, right? Now, when you build the object from the by the SLA process, what you will do? First you will according to the slicing different, first you cure this particular layer, next you cure this layer by rejecting next this layer, this layer, this layer, this layer you will cure. Now when it will reach this particular point, it will cure this particular portion and also it will cure this portion. When you reach here, it will cure this particular portion by laser tracing this part portion, then this portion, this portion, then this portion, then this portion, this portion, then this portion, this portion. The total thing will be cured. Now, but when you start curing here, if below that it is liquid resin, once it will cure, it fall down here with this orientation. Because below that there is liquid resin, then what you have to do in a CAD model itself, so you have to create a geometry, that is the support structure. You have to create a geometry of a relatively lighter in shape so that from the bottom itself, this particular structure will cure and it will provide the support for this particular layer. This is called the support structure that you might see in case of a water tank in civil engineering. Water tank, this portion there is no support, central portion no support structure is required because it is built from the ground. But once it is overhang portion, you need support structure from this type of support structure is required in civil engineering. Same concept is here also. Overhang portion for certain additive manufacturing like SLA process, you have to develop the solid model of the support structure before slicing, and support structure will also solidify along with the build portion, along with the main part portion, so that this portion will provide support in the overhang portion. Once your part manufacturing is over, remove the support structure by traditional tools. Remove that support structure by traditional tool and then you go for the full curing operation. So this is the importance of the support structure. Next will be your important thing in the layer thickness. So layer thickness has big role in a product quality as well as the product quality is surface roughness here. If your this particular shape, if your layer thickness is high, in a curved shape portion, stair stepping effect will be more. Whereas if your layer thickness is lesser, stair stepping effect will be less. This is the one effect. Another effect is orientation also big role. Orientation has a big role in the product quality. If a particular, though I have taken a very simple example to show you the concept, if you like to create a half cylinder by additive manufacturing process, if you orient like this, and you do the slicing, each slicing your cross section is rectangle, but width is different. Length is same, height is obviously same, it is equal to thickness. Width is varied because it is a curved shape. See, curved shape. And because of that, when you deposit the material, this curved portion there is a stair step effect. But if you orient your object not in horizontal, but vertically you orient, then you do the slicing, then each cross section will be your semicircle of same diameter. That means if this edge there is no variation of the diameter, as there is no variation of the diameter, there will be no such stair stepping effect. So these two are important. One is the layer thickness, another is the orientation of the geometry before slicing. Orientation of the geometry before slicing have the two roles. One is the minimum number of support required many times, and minimum stair stepping effect may occur. So part orientation before slicing is very important. SLA process is also used in micro SLA for the medical, dental application, jewelry application. We have to skip that part. Next is the that I mentioned in the last method also, the process parameter for this process. Wherever laser is used, very simply you can remember that the laser power, scan speed, and the laser beam diameter along with the layer thickness is the important process parameter. Along with that, curing time and the bar orientation, hatch spacing, and the hatch pattern. So these are the important process parameter. And what is the advantage? Advantage is highly accurate product can be manufactured. Surface finish also high. simple and compact, multi-material capability there, micro manufacturing is possible, but disadvantage is machine is proprietary machine, so machine cost is high, material cost is also high, there is material limitation and support material is required for the overhead portion, so that is why the wastage of material is more. Poor mechanical property because it is made of only the resin material. So next is a very popular one because the self-learning mechanism and the less costly. That is the material extrusion based additive manufacturing process, and process is the fused deposition molding or FDM. Now FDM is I think most of the engineering college FDM is available. It is your material extrusion process, cost development strategies, USA. And the material used are basically ABS, PLA and different kind of your polyurethane or elastomer. Again, your basic thing is pre-processing. After pre-processing, you have to do the main process. In this case, the platform, this is the extrusion head. Extrusion head is temperature control and position control. Though it is the one kinematic or one variant, extrusion head is position control. That means XY movement is there in the extrusion head and Z movement is provided in the build platform. Now there is a set of roller and this is the input material and feedstock. Feedstock is your filament form, the polymer filament. So filament is your either made of PLA or your ABS or many other material is available nowadays. And its diameter is 1.25 millimeter, fed into this chamber through the roller, and due to the heating here, it becomes semi-solid, and due to back pressure, continuously the roller will rotating and it will creating the back pressure inside. Due to the back pressure, the semi-solid material will deposited or extruded from the nozzle of 0.4 millimeter diameter. Nozzle of 0.4 millimeter diameter, it is extruded. As this is moving in a XY direction, depending on your cross-sectional information, so it will deposit the material. How will deposit the material? First will deposit the material outer layer, then inner layer, and inside also it will deposit like this. Just like you take a toothpaste, you open this one, and you just deposit the material. Outer boundary, inner boundary, and inside. So it is sometimes jokingly we are calling this is similar to your jalebi making machine. Jalebi also same thing, though it is geometry, the 2D simple geometry, but process is similar. This is your nozzle, back pressure is created by hand, and hand is also XY movement, and then the tip there is a nozzle, semi-solid material will deposit. The same thing happened in case of a FDM machine. So it will deposit the material. Once one layer is over, platform is lowered down, according to the second layer processing information, again head will move in XY direction and deposit the material. So here no laser, nothing, so that is a very simple mechanism. Now if there is a single nozzle machine, there is a dual nozzle machine. Dual nozzle machine having advantage. Dual nozzle machine you can use the two different material. One for the build material, the blue color is the build material and the red color is the support material, because here also support is required for the overhead portion or cantilever portion. Support is required. If you use the different material for the support which is weaker than the build material, then you can easily remove the support material. Ultimately support material you have to remove. If you can use the different material than the build material and the support material if it is weaker, then you can easily remove. Many times support material is the aqua soluble material. You dip into the aqua medium, it will dissolve. So that will be better if you get the better surface finish in this particular area. So this is very popular. Dual nozzle machine is very popular. Though it is not relevant here, time is also short. Let's skip this one. So here is the animation of the your typical FDM machine. So it is the animation of that.
Additive manufacturing process that uses production-grade thermoplastic materials to produce both prototype and end-use parts. This technology is known to accurately produce
So this is a two nozzle.
excellent strength ideal for concept models,
depositing the material,
manufacturing aids, and low-volume end-use parts. The FDM process begins by slicing 3D CAD data into layers. The data is then
this is the two your cuttings.
layer by layer.
One is for build material, another for the support material. This support material cutting, this is the build material cutting, or the, this is not a cutting, it is a spool.
Plastic and support materials are used to create each cross-section of the part. Similar to a hot-melt glue gun, for the material.
Build material and support material.
Nozzles. The extrusion nozzles precisely laid out will support
So it is exaggerated view.
on the preceding layers.
So white color is the support, black color is the build material overhang portion. You see, this is the white color is the support material and black color is the build material.
Continues to move in a horizontal XY plane while the build platform moves down.
So once one layer deposition is over, build platform is lowered down equal to one layer thickness according by axial movement of the platform or the axial movement of the nozzle, you will get the layer. So once it is over, now you have to remove the support material.
Service providers such as Solid
You have to remove the support material.
to create smooth surface parts including hand sanding, assembly, and cosmetic paint.
So this way you can get, but obviously the surface finish will be poured as you have removed by the support material by traditional means.
And all
So next, quickly let me show you. This is the during the COVID, we have developed our 3D printed mask by our tabletop machine. Here you see XY movement is provided into a head, and intermittent jet motion is provided to the platform. And mechanism here is the screw nut mechanism. And in case of XY movement, the mechanism is your timing belt pulley mechanism with the linear guide and timing pulley belt mechanism. Okay. Same thing once again, let to show you here. See, XY movement is given here. Intermittent jet movement, it is very difficult to understand because layer thickness is very small, you cannot see the naked eye. Next will be, this is the soft mask, because that particular mask is the hard because they made of ABS. This is the elastomer. The polyurethane rubber is used to deposit, and this is the flexible face mask developed in that particular time. Next will be the only the picture for taking snapshot only. Okay. So this is the machine, and the product we have used for a few days. Okay. Few of the students, myself. So next will be your similar kind of things to develop. Though the CAD model, getting CAD model of this one is not easy task. Previous one CAD model we have developed, but this one CAD model we have taken from the GitHub or that particular website, got that one. So you like to skip this particular part, same thing is there. Now we go to the, in this particular process you have seen, you can see in this model, the nose portion, this portion, there is support structure. This is the support structure basically. Nose portion is over and you need support structure. What problem you have faced, when you just remove the support structure, there is a damage on the particular nose and other part. So it is the requirement from the industry that can you not develop any FDM system which is supportless FDM process. And there is a role of robotic 3D printing. There is a role of robotic 3D printing. Using robotic 3D printing, you can develop the supportless FDM printed product. You just see here the robotic head is used to deposit the material over a build platform. It is also a robotic platform which having certain axis, orientation. This can control the orientation. It can control the orientation in such a way, always it becomes horizontal. Always it becomes the horizontal, so that even in an inclined one, you can deposit, if not make it horizontal, then you deposit. So that is the interesting thing. This robotic additive manufacturing or robotic 3D printing now becoming the very popular because it can create the support-less 3D printed component that was not possible previously with the traditional CNC-based 3D printing. The 3D printing that I have shown previously for mask making and other, that is traditional CNC-based Cartesian 3D printing system. And this one I am talking about the robotic 3D printing. Process is same, FDM, but it is a robotic 3D printing. Use of robotic 3D printing, most important advantage in respect of FDM here, for overhang portion, no support structure is required. Without any support structure, you can develop, because whenever you like to create any overhang portion, you make your platform that much of angle, reverse direction, so that it becomes solid. So through the NX simulation software, you can see this is the robot used for FDM process, and this is the total thing, the package. Here is the build platform. Build platform is not like only Z movement. Build platform having also the X, Y, Z movement, about rotation, X, Y, Z direction rotation, just like a wrist, just like a wrist.
The use of robots in additive provides larger work envelopes, often eliminating the need to divide parts into multiple pieces.
See the robotic printing, but obviously that here the slicing is different. No traditional slicing will be used in this case. That is for Cartesian. Your 3D printing system slicing is done. Here the slicing is different. This slicing is called the conformal slicing. So process parameter. So the process parameter is the layer thickness, bed temperature. So these are the process parameter. Advantage here in case of FDM, the low cost, simplicity, and ease of use, easy material change, less material wastage. But disadvantage is the poor surface finish. Needs the support structure if you use the traditional additive manufacturing system. Next is the most promising one, the powder bed fusion method, PBF, powder bed fusion method, and one such machine is the selective laser sintering machine, and obviously name itself says powder bed fusion. Over the bed platform you have to spread the powder and you have to fuse the powder. From the name itself, powder bed, that means over the bed is built platform, you spread the metal powder and fuse the metal powder. In order to fuse the metal powder, you need the heat source. Heat source is laser here. Laser beam is your heat source. So the process I like to explain here quickly. See, same thing. There is two chamber. There are the different variant, but two chamber. One is your powder delivery chamber. Another is the build chamber. Build chamber initially platform will be here, and the powder will be heap of powder. The heap of powder will be here. Now being a roller or the spreader, whatever you call it, using the knife, you have to spread the heap of powder over the build platform, and you create a layer of powder whose layer thickness is safe. During your slicing, if you put a layer thickness is 0.01 millimeter, then you put it that particular thickness. That amount of powder you have to heap up through this movement of the piston and spread over that. Now, according to the processing information, same as SLA, the laser source, there will be optical system, laser will tracing the cross section. The cross section is this one. Again, the same issue of SLA. Laser will trace the outer boundary, inner boundary, and inside also laser is tracing. And due to the interaction of the laser and the powder will fuse and adhere with each other, and it will create the one layer. Once one layer is over, the build platform is lowered down equal to one layer thickness equal to 0.01 millimeter say, and at the same time this side it will move upward direction, so heap of powder will be here, again through the your roller it will spread over the previously sintered layer and you will get the second layer powder. According to second layer processing information, again the laser will traces the complete path, outer boundary, inner boundary and inside contour. So again, and laser power is controlled in such a way, it not only sintered the second layer, it will create the bonding between the second layer and the first layer. Once the second layer is over, again this build transform is equal to lower term equal to one layer thickness, this is move upward direction and process will continue till topmost layer is come. Till topmost layer will reach and you will get the product. But one interesting thing here, this portion is the overhang portion. Overhang portion, there is no need to support structure. In case of a SLA, studio lithography apparatus, this overhang portion below that there is liquid, so you need the support structure. But here it is a powder. Powder having sufficient strength to provide the support of this overhang portion once it's sintered. So that is why powder-based methodology, powder-based additive manufacturing is a very promising one because the weightage is very less. Moreover, unsintered powder, this unsintered powder can be reused. So that is a powder-based method like PBA, powder-based solution is very popular method and it is one of the promising additive manufacturing in metal additive manufacturing as well as the in your polymer-based additive manufacturing process. So here we like to demonstrate that particular method. Please. This is the metal additive, metal and here the powder is metal powder. So this is the interaction of the laser and the powder. Sintering process is over, one layer is over, then the powder will spread.
A variety of metal and alloy materials, such as stainless steel, cobalt, chrome, and nickel, to create strong, durable parts and prototypes. DMLS is an excellent choice for functional metal prototypes, high temperature applications, and end-use parts. The DMLS process begins in the same fashion as other layer additive manufacturing technologies. A program takes 3D CAD data and mathematically slices it into 2D cross-sections. Each of these sections will act as a blueprint, telling the DMLS machine exactly where to sinter the metal material. The data is then transferred to the DMLS equipment.
So this is the machine, though it is the animation kind of thing. This is the spreading of powder, then laser stressing, then lower down the platform, then spreading of powder. This process will continue till topmost layer will reach.
Once a single layer is complete,
Spreading, laser stressing, platform lower down, again spreading, laser stressing is process.
reported equally on the previous single layer. The DMLS machine continues to sinter layer upon layer, building from the bottom up. As the part is built, support structures are added to give supplemental strength.
See, there is no support structure. Nothing is visible. So this is the product developed based on the polymer here. Next, this is the process parameter. Obviously, as there is a laser I mentioned, if there is a laser beam power, laser beam size, and laser beam speed, and layer thickness is the common process parameter for most of the process. Next is the advantage. Powder reusability that I mentioned, no support structure is required, high mechanical property is possible, and any small critical complicated feature is possible because laser beam diameter you can control to the very small level and micron level. So that is a small feature you can create, better dimension accuracy is possible, better surface is possible in MDM process. What is the disadvantage? It is the thermal process. Obviously, there will be existence of thermal distortion and porosity. So, this is the two biggest disadvantage of the powder-based fusion method. But researcher is working on this particular area. All over the world, they are working in this particular area so that defects. This is the defect basically, like welding defect. This is the defect. Defect should be as minimum as possible. Next process is the binder jetting. This is also powder is there, and the binder jetting based method is first developed by MIT Boston, and their product name was the 3D printing. Now we all our machine are calling it 3D printing, but it is this particular term is coined by MIT first in their product. Here their product similar to previous one powder bed, only difference is previous case there is a laser will dressing over the powder, laser will space and it will fuse. But here it is a cold additive manufacturing process, no thermal process, no such thermal process. Instead of laser, the adhesive will be deposited selectively so that it will adhere. So small part for demonstration or for show pieces, this type of additive manufacturing process can be used because the powder will adhere by adhesive, not by laser sintering process. So that's the difference, nothing else, if you compare with the previous one. But it has a lot of application of the industry that I will show you. Because there are certain applications, no such high strength component is required. So that one such example I like to show you after this, that will revolutionize a particular area. This is the method, you just say, the machine. This is the XY movement of the deposition head, binder deposition head. The white color is the powder. Here also another advantage, here the same advantage, no support structure is required. So it is a powder bed only. Instead of laser there is glue. But strength of the component is less. See, no support structure is required, powder can be used, so these are the advantage. But one interesting application of this one I like to show you, very interesting application. That is the application of this binder jet additive manufacturing process in foundry industry. Okay. In foundry, as you know, in a sand casting process, traditional way, first you have to make a pattern made of wood that depends on the skill of the pattern maker. Then you have to make a mold, that also skillful. Okay, it will time consuming as well. Okay, and then you will do the casting. This is the long route. That chain can be reduced by directly print the sand mold. Directly print the sand mold only for that purpose. The solid model or the CAD model of the product geometry or the product is required, because if you have a CAD model of the product, reverse part of that will be a mold. Product you know the model geometry. Reverse of that will be your, or negative part of that is your mold geometry with some allowance you provide. That CAD model is this one. This CAD model will be the input for your this the binder jet 3D printing machine. Okay. Because when you like to do 3D printed sand mold, no such strength is required. Only thing is it is made of a sand and with the proper property. So no such skill is required of the skill of the your carpenter, skill of the mold maker is not at all required. Only you need CAD model of the product. Only you need CAD model of the product. So this is the negative part of the CAD model of the product, that is the mold to CAD model. At a time, as the giant machine, at a time number of mold can be printed, so that is why same mold has been copied here, or different kind of mold has been stacked one after another, because the machine that I like to show, that is a big machine, not a small tabletop machine. It is an industry grade big machine. So this is the machine. So pre-processed data is fed to the machine. Now you see this is the hopper. This hopper means not hopper, sorry. This is the print head. Through this, there is a tiny nozzle. Through this, glue will be deposited. The binder will deposit selectively. Wherever it is required, it will deposit. So this is, if you see, there is a fade of color. It's not a white color. Once deposited, you see the color is some yellow. So that is basically glue. That portion. Now there is a hopper. It will basically spray the sand. The fine sand will spray over here. Previously glued layer, now it is full white. Next, this will come and it will deposit the glue according to the cross section. This way it will continue till top of layer will come. So wherever the brown stick, that means glue will be deposited selectively. So this way your deposition, spreading of sand and depositing in glue or binder will take place. Next, what you do, no support material is required again in this case. And by your vacuum cleaner, you take it out of your unglued sand. Then you take it out your mold, 3D printed mold. Now nothing is required, no skill of your pattern maker and the mold maker is required, only CAD model. From the CAD model directly print your sand mold. So some post-processing operations like cleaning, free sand you have to remove from the cavity. And mold has been created by splitted form. Maybe some specific reason might be there. So you have to assemble by traditional way. You have to put the core inside. So next we get the casted part. Now application of robotic system or serial robotic manipulator for same purpose. Palmer is the manufacturer of this. So this is the serial robotic manipulator which is used to create the sand mold, treating the sand mold in industry. This is the same special head which consists of both the spreader as well as the fine sand spreader as well as the dispenser of the glue. Glue is a colorful glue is used to make a colorful product. So I like to skip this part. This is the application of robot in creating the 3D printed mold. Process parameter, again here the layer thickness, then binder saturation and scan speed, detail power and so on. Advantage, no support structure is required, it is not a thermal process, no wrapping, and multi-color part is possible. But disadvantage act is binded by the glue, some poor mechanical property, need for post processing, but there is sinking problem in the loop. Next is the material jetting. So material jetting is also jetting the material from the nozzle, obviously it should be liquid material, liquid resin material. Now I like to show you the process. Process is first it will depending on your cross-sectional geometry, from the nozzle selectively deposit the material liquid resin followed by the UV light curing. So I like to first, it is a statistics machine. This is the machine, it looks like this one. Machine cost is available in senior Durgapur. Its cost is around 1 crore. Okay, and the running cost is much more higher because the cutting and the material cost is so high because of the proprietary material. And I like to show the working principle of that first. But very precise components you can manufacture with a reasonable accuracy.
Polyjet is a layer.
So this is the polyjet. You see this. This is the UV ray. Before that there is a dispensing unit. It is a faster process than the SLA.
Physical prototypes. Polyjet is one of the fastest prototyping processes available to develop high-precision physical parts and is ideal for smaller parts, cured smugglers, and faster patterns. The polyjet process begins by slicing pad data in cross-sections or layers, extended to 6/10,000ths of an inch.
The slicing cross-sectional information.
Data is then transferred to the polyjet machine, which begins constructing the object one layer at a time.
Now see, this is the depositing the material followed by UV cure. Depositing material as well as followed by UV light. So depositing material by this tiny nozzle. You see, deposit the material selectively followed by the UV curing. Its process is very fast.
Simultaneously cures material as it is printed. Once the cross-section is complete,
No such post curing is required. In SLA there is a post curing is required because it is amount is within the regime, but it is over the ambient temperature, ambient atmosphere. That's the difference between the SLA and this particular process. No such post curing is required in this case, but in SLA it is required. Regime may be same, but process is different.
options are available from service providers such as Solid Concepts. Polyjet parts are well suited for quick, economical prototypes, requiring
So these are the process parameters. We quickly move that one. Even you see, I just manufacture this small part. If you see the length of the finger, this small part cost is 5,000. Including GST, the similar charge this much of cost for manufacturing this one. So accuracy is very high surface finish, multi-material part can be possible. There is a easy removal of the support structure, but disadvantage is poor mechanical property. This I did mistake here. The process is relatively high in speed with respect to SLA, not a slow process. And support structure is required, obviously material wastage will be there, high cost of the material as well as machines. Next, last one, but not the least, very important one. This is the metal additive manufacturing process. PBM is also metal additive manufacturing process. Here, metal as well as polymer, but this one is basically restricted to the metal. So metal additive manufacturing process is directed energy deposition. Directed deposition, there are two types. Based on your feedstock, that means in feed material, either it will be your powder based DD, in short I just mentioned here. Let me see this slide. So DD, total process DD, it is either powder based DD, powder DD or the wire DD. If your initial material is powder, then it is called powder DD. If it is the wire, then wire DD. Now the powder DD, first we like to focus on the powder DD. This is the powder DD. Forget about this classification. Let's see this one. Powder DD process. So there is specially designed nozzle. You just see when the powder will flow through the carrier gas through the nozzle, centrally laser will pass and they will make after that nozzle tip of the nozzle. After just below the tip of the nozzle, centrally flow powder and circumferentially flow powder and centrally focused laser will make and it will create the melt pool and it will deposit. It will melt and it will melt the powder and it will deposit. So this is the difference between the PBA powder bed fusion and the DD. Powder bed fusion, powder will spread over the bed and then laser will pass. But in this case, specially designed nozzle where powder will flow through using the carrier gas from the powder stack will get a different distance from the machine. And you just see, this machine has a lot of flexibility. Any complex change, any repair work can do by DD process, and it is robotic system. In Cartesian system is also available. In CNI itself developed a Cartesian system, but most popular one is the robotic one because you can use for repair purposes. See, this is the flow of powder circumferentially, centrally laser. They will make somewhere here and melt pool will deposit it selectively wherever is required. That you will see any complicated object over any curved surface or over even in the curved surface you can deposit the material. You can do any kind of repair work. If certain portion of the gear tooth portion has been old now, you can deposit the material using this process. That is not possible in case of PBA, powder bed fusion. Powder bed fusion that we just discussed is only additive manufacturing process. But powder DD is both additive manufacturing process as well as it will work as a repairing a machine for repairing or dynamically repairing methodology. So let us see this one. Method is this is your powder. This is the powder feeder. Powder will feed to the special that I mentioned, the nozzle through the pipe carrier gas. Centrally the laser, they will melt and create the melt pool and it will deposit. Where it will deposit the filter. And this one you can give extra movement here or you can give extra movement here. It is up to you. You can give extra movement here and Z movement here, or you can give extra movement here. Okay, so below is the Z movement. So different kinematics is there. So this is the example that CMR has developed a machine. This machine has been developed by CMR has developed. It is the XYZ. This is not robotic system, but it is the powder DD based. So typical robotic additive manufacturing used in the industry. This is a powder DD process. Over the existing component, some repair work is done by powder DD process. Basically, it is the extension of the laser cladding process. This powder DD is the extension of the laser cladding. Laser cladding one or two layer, here multiple layer. So this is the machine. This is the powder system, powder feeder system, and this is the specially designed nozzle, circumferential groove and central groove for the laser. So this is the lane system. This system is also popular. This is a powder feeding system. Optomat lens, a very popular machine. So next I am going to move quickly to our next process. Next will be the wire-based DT process. Now wire-based DT process, input is the wire and you have to melt the wire. For that, arc is one option, laser is another option, or electron beam is another. Wire arc anti-manufacturing process is nothing but extension of the welding process. Where in welding you will deposit one or two layers, here multiple layer you deposit, you will get the 3D component. So it is either D wave or T wave. This is the picture which is the robotic wire arc manufacturing setup at senior as well. So this is the welding robot. Now welding robot is used for robotic wire arc manufacturing.
We have developed the most outstanding hard-welding robot on the market. The ATAL-FDP-Session, the ultimate hard-welding machine.
ঠিক আছে
I've shown you the top 6 sales arguments for the IRB-16.
So I like to see this time shot. Let us quickly explore this one. Quickly it will show 40x speed or 400x speed, something like that. Fronius setup for the welding. And say though it has been shown 400x speed, layer by layer the arc MIG welding is used to deposit the material to get the 3D object. But disadvantage is surface finish is extremely poor in case of a real time it is 4 hours, here it will be 30 seconds. 30 seconds has been shown 2 hours job. Now I like to show this setup where okay, this somehow picture is not coming properly video. So this is the setup in senior as for 3D printing setup. This is 3D printing using the robot and the Fronius welding system. This is the Fronius welding setup. This is the wire feeder. Stainless steel wire is used. I just including the now process parameters like powder DT, the beam power, scan speed, beam spot, very important, material feed rate or flow rate, powder property, powder size, shape and distribution, in case of a wire, in wire DD standard height, that is also an important process parameter. Now, in general, advantage is high deposition rate is possible, dense and strong part can be manufactured, multi-material is possible. But disadvantage for both the process porosity and thermal distortion and low dimension accuracy and very poor surface finish in case of a wire process. So we have discussed the different additive manufacturing process here. So I think covered all 7 additive manufacturing process. Now we like to end up with a few more. So one is the some kind of hybrid additive manufacturing. Hybrid additive manufacturing means additive manufacturing along with the traditional metal cutting or the laser based processing, so that post processing also do simultaneously. So I like to skip this video. These are the company. You just see this is your pattern here. This way you can create the supportless additive manufacturing, and here the setup is hybrid system. Traditional additive manufacturing as well as your traditional manufacturing, measuring device, everything is in a single setup. This is another type of additive manufacturing which is developed by the HP multi-gate fusion technology. HP is the giant manufacturer of 2D printer. Now they are in the business of 3D printing. And see their printing technique.
Unlike the slow print processes of some current technologies, HP multi-jet fusion technology's proprietary area-wide processing achieves quality part production at speed. The process begins by applying a layer of material in a work area. In the opposite direction, in one continuous mass, we print fusing and detailing agents across the full working area. This pass combines the printing with the fusing energy, and the process is then completed. HP's proprietary architecture is capable of printing 30 million drops per second along every single inch of bed width, enabling precision in dimensional accuracy. To produce truly functional parts, it's important to ensure that the material has been properly fused and that part edges are smooth and well defined. To achieve part quality at speed, HP invented a multi-agent printing process. In this process, the fusing agent is applied on a material layer where the particles are meant to fuse together. A detailing agent is applied to modify fusing and create fine detail and smooth surfaces. The area is exposed to energy, and reactions between the agents and the material cause the material to selectively fuse together to form the part. The fusing process requires accurate temperature control across the entire material layer. HP Multi-Jet Fusion's closed-loop thermal control system does this by measuring temperatures at hundreds of points on the material bed. This information then determines which areas receive more energy to raise the temperature and which areas are cooled, allowing for control of thermal bleed and layer-to-layer fusing and cooling. The result is full control over mechanical properties, dimensional accuracy, and repeatability. The process is then repeated until a complete quality, truly functional part has been formed. This is how HP's proprietary area-wide processing compares with existing popular point processing technologies for building functional parts. In the time it takes slower point processes to build one part, HP's multi-jet fusion technology can produce functional parts in a fraction of the time. Using HP's proprietary multi-agent printing, HP multi-jet fusion technology achieves new levels of part quality with uniquely predictable print times for any type of part to drive optimized production and design freedom.
So now it is a very old status. So these are the area where the additive manufacturing, aerospace is 18-19%. Even in the automobile sector, around 15%. Your medical sector, there is a significant amount, like 11%. Where the consumer product is 12-13%, so on. Now the recent trend, it is exponentially increasing its application in manufacturing. Advantage that as I mentioned, the complexity of structure, any kind of complexity geometric structure can achieve by additive manufacturing process. In other way, you can say the geometric complexity is free for additive manufacturing. So it's not at all an issue. So that is why any additive structure inside, any uniform structure inside the component can be achieved very easily. And because of that, you can create the optimized geometry, you can create the low weight component generally used for aircraft, and with the less material consumption and ultimately the less energy consumption. That is possible. That is why aircraft industry is basically mostly user of the 3D printing currently. Small batch size of the customized product are economically attractive related to the traditional mass production method. And another is the additive nature of the process gives the material saving and does the ability to reuse the material, unused material. Okay, so less wastage in most of the cases. Direct reduction, direct production from 3D CAD model means that there is no such tools, no such molder required. And it can manufacture anytime, anywhere, and customize. This is very much applicable in 3D printing for the mass customization, not the mass production. Customer specific implants, say medical, for that this is very. So wherever you need mass customization, additive manufacturing process is beneficial to you today. But what are the drawbacks? There are a lot of drawbacks or a lot of challenges in additive manufacturing. First challenge is the material option, very limited material option. So next is the strength issues. Whatever strength you get in a traditional manufacturing process is not yet achieved by the additive manufacturing process. But research is going on all over the world to improve these two areas along with the accuracy and surface tension. And other areas like online condition monitoring, metrology for additive manufacturing, so it is also a very hot topics in the area of research. This one, those were design engineers for them. Design for additive manufacturing is a completely new area. Okay? Design for manufacturing, you already know, that is for traditional manufacturing. But design for additive manufacturing is still it is in a very niche stage. You have to think more on that particular area. Understanding of science of additive manufacturing is another area of research. Optimization of process parameter is obvious for any manufacturing process. And then speed and cost reduction, speed increment and the cost reduction is another limitation, because now speed is not up to the mark, cost is high. So with this, thank you for patient hearing. If any queries, let me know. And before that, I like to give Kaushik the second chance.
Okay, some of the participants wants to ask questions.
Okay, second chance for you.
Related to the disadvantage, you have mentioned that porosity one disadvantage for actually SLS and some other.
Thermal based additive manufacturing, porosity obvious.
The disadvantage means porosity is porosity is more, right?
Porosity more. But plastic welding process. Any other thermal process. By controlling the process parameters, we can reduce the porosity.
So porosity means related because of means emerging of gas.
Emerging of gas. Even thermal process, if you the gas entrapped within that, because of that,
In general, say for example, fuse deposition modeling. So inbuilt there is a parameter like infill amount. So there is a
infill amount 100%.
Okay. In case of that also.
That case I am talking about.
Okay.
Infill amount 100%. Suppose I need a product with the infill density 100%. There is no porosity, no such honeycomb structure. If there is honeycomb structure, there is porosity is not an issue. But if I need a solid component, then
Sir, in case of arc welding, that powder fusion, that process, in that case, the temperature is not problem, means the previous layer is hot already, then we are doing this, then how it is done, and another thing is that what is the minimum thickness achievable, or
actually WAM process is the extension of the welding process.
yes,
The welding process is a very crude process.
yes,
Everything is crude process. If you go for the laser welding, to some extent is precise, but arc welding is a very crude process. Big product is manufactured by WAM process.
yes,
Big product, not at all a precise product. Big product means the bridge you have to manufacture. Steel bridge you might see in the UK or something. Newspaper I have seen. Steel bridge has been made by the WAM process. Bridge means a big one.
yes.
So their surface finish accuracy is not a issue. That time a WAM is used. That time layer thickness and the accuracy is not that much of issue. You have to do machining. And WAM process followed by machining. No way out. WAM process followed by machining. You have to do machining operation.
Okay. After that machining.
Machining is required 100%. Without machining, WAM process there is no use. Whatever product you will see, you will get, that is no use.
And will there be any time gap between the first layer and the second layer, so bottom layer?
That is obviously it is the issue for the research point of view. It is the issue. Depending multi-material, if you use, there is a time gap required. If the same material also, otherwise there will be no such metallurgical bonding.
Yes.
In order to give proper metallurgical bonding, you have to maintain that one. And that particular area everywhere, and those who are working in the WAM, they are working in that particular area. But there is no such standard data book for that. Even in the emerging areas,
Yes.
no such standard data book is available. Only you have to base on the literature itself. Literature, you will get the data. No data book is available till today.
Sir, I have 2-3 questions.
Three questions.
One question is that the tip that you are using for depositing the material, while laser will focus ultimately and material will deposit, that area taking heat too much, and that distribution, have you seen or done any work on that?
Power DD process. Power DD process.
Parodies process.
This is the powder DD process. Circumferentially powder will flow and centrally laser, and
Yes.
then it will meet with each other just below the tip of the nozzle. That time there will be an interaction between the powder and the laser. Molten pool will create. Obviously, heat zone is the highest one.
Yes.
That particular area.
Yes.
And that will deposit it over the previously deposited layer. And obviously there will be heat transfer.
That heat shifting is very much troubleful. One. Second one is the initially welding is a fusion process of joining. That two material dissipate heat by welding. At that, in that case, no rod or heat deposition, air is automatically sucking the heat. But in case of 3D printing, if you deposit metal every time or join metal by any means, heat dissipation is major problem.
Heat
That-
dissipation will take place at the same time.
Accuracy.
And heat dissipation is not that much controlled way, so that is why you are not getting also strength. That is a big issue.
Big issue.
The 3D printing, even powder DD, whatever strength will get, that is much lesser than the any product you develop by traditional manufacturing.
Yes.
because that issue has not yet solved. That issue is not yet solved, and that is why worldwide the metal 3D additive manufacturing process is working in that particular area. How to control the heat dissipation, how to improve the mechanical property and metallurgical property of the product.
Because
this is a very important research area in the additive manufacturing.
another point that we have got, that whatever manufacturing we are doing, the accuracy, it is producing layer by layer, contour structure. If you do even a gear, contour structure, whatever you are doing, that requirement machining ultimately. Otherwise, the
But the additive manufacturing process is not for manufacturing
primary
the gears,
process, yes,
not
yes.
for the manufacturing of the gears.
Not for the gears actually.
It is not for the manufacturing of the gears. The gear is a standard geometry, standard everything
geometry.
is standard.
Conventional
If your gear is such that inside there is honeycomb structure or something, you have to make a gear with a low weight for aircraft application. Then you can use the 3D printing. But if you use the solid gear, 3D printing is not a good choice. Still that 3D printing is not a good choice. When your traditional manufacturing process will fail, then you can start thinking for the 3D printing. Traditional manufacturing process fail means your geometry is so complex that your traditional manufacturing process is unable to manufacture. Then you think of 3D printing. Another thing, when mass customization is required, mass customization, patient-specific implant, like my implant shape and size is different from the other patient implant size. There, if you like to manufacture by the traditional manufacturing process, for each implant you have to make a mold or die. Die cost is maybe 2 lakhs. Metallic die cost maybe 2 lakhs. Then how much is the cost of the implant? More than 2 lakhs. But if you use 3D printing, within 50,000 you can manufacture, because there is no need of mold or die for 3D printing.
Yes.
In 3D printing, if you manufacture one component, that is also 50,000. If you manufacture 5 lakhs component of same size, that is also 50,000 each. But in case of a traditional manufacturing process, if you manufacture one pen by means of a die, because if you manufacture this particular pen, you the die, that die cost is say 60,000. If you manufacture one pen, the pen cost will be 60,000 1 rupee. But if you manufacture within using that particular die, if you manufacture 6 lakhs pen, then how much is the pen cost? Maybe 5 rupees, maybe less than that. But that theory is valid for the traditional manufacturing because they are use of the die. But in additive manufacturing, it is the die-less, tool-less manufacturing process. So that is why all product, means if you manufacture this pen by additive manufacturing process, cost is 20 rupees. If you manufacture one, then also 20 rupees. If you manufacture 500, then also each 20 rupees. If you manufacture 6 lakhs such pen, that also 20 rupees each pen. Because there is no such die cost and tool cost.
All is variable cost.
No such fixed cost is imposed on that. All are the recurring variable.
Another thing that you have shown a art photo at CMERI is building. Are they really building that art?
Which one?
The art photo.
That's not CMERI, that is
It's
net.
outside, okay. And any
Oh,
biogel.
the art in CMERI part, that is in not, it is in Kolkata, there is a center, I forgot, Fuji Wearable Center. From
Okay.
there I got the book.
Okay.
They have manufactured. That art is solid art.
Solid art, okay.
Not the biogel art.
Okay. Another one, the biogel that you are taking.
That is I
the
have taken from the net. The biogel is used in China as well as in.
Oh, that is too much complicated.
Biogel they are.
Thank you.
Any other questions from participants?
What is it?